Hi everyone, and welcome to our Chemical Engineering 470 capstone presentation on the conversion of 1,3-butadiene to styrene. We are Team 9, the Spectacular Separators, and our team consists of myself, Randy Grimm, along with Corey Betts, Katie Corradoni, Sarah Bien, Eric Remington Lee, Li Wen Shi, and Bryn Stewart. Our presentation today will focus on three main components. The first of these components will be the location and capacity of our facility, along with the products that our plant produces and the specifications for these products. We will then move on to talk about the process flow of our plant, along with the environmental concerns that were considered in the plant design. Finally, we will end with the economic feasibility of our design and make a recommendation for the progression of this project in the future. Our team works for Knitline Chemicals, which operates in 3 different locations. The first of these locations is Houston, Texas, which is where our plant will be built as an extension of the facility that currently exists there. This plant is on the ship channel, so it has easy access to pipelines, which will supply the raw materials. Our next location is in State College, Pennsylvania, which is the research and development facility. All of the project development and design that is discussed in this presentation was done at the State College site. Finally, our last location is in Philadelphia, Pennsylvania, which is located on the Delaware River. This location has easy access to ship and rail transport, and it's also the home to our small pilot plant. I will now hand the presentation over to Bryn Stewart, who will discuss the capacity and products that our plant produces.
Thanks, Randy. So our plant station in Houston, Texas has a production capacity for 664 million pounds per year of styrene. And this comes from a feedstock stream of crude C4s, which is made up of butadiene, isobutylene, 1-butene, N-pentane, propylene, and N-butane. This feed stream is over 50% butadiene, which is the component that produces our styrene product via 2 sequential reactions. The first reaction converts 1,3-butadiene into VCHX, and the second reaction converts VCHX, which is vinyl cyclohexene, into our styrene product. So our overall process will be covered in more detail later in the presentation. Right. So our process met all of the hard specifications for our products. However, we only met 2 of the 4 performance targets. While we met the targets for overall selectivity and the restriction on cooling utility for the distillation columns, we did not meet the soft specifications for VCHX losses nor the distillation tower energy maximum. In order to reach the target for the VCHX losses, we would have to incorporate many additional units into our process. And the benefit of reaching this target did not outweigh the capital cost and the additional equipment that this would have required. So for the distillation tower energy requirement, we added a column to purify an extra product of benzoic acid, and our high energy columns in the rest of the process allowed us to reach high purities for our styrene product and the benzoic acid product. So therefore, we reasoned that meeting this target was actually justified. Not meeting this target was actually justified. And overall, we were able to produce styrene at a purity of 99.96% at a flow rate of over 79,000 pounds per hour. And in addition to our main styrene product, we were able to produce benzoic acid at a purity of 99.76% and a flow rate of over 1,800 pounds per hour. And finally, given that our feed stream was made of crude C4s, several of our waste streams were able to be converted to fuel at a total rate of over 9,000 pounds per hour. And these streams can be further integrated into our process to save us costs on utilities and energy. While Knitline Chemicals has been a producer of butadiene in the past, our R&D team has determined that the demand for butadiene is falling. So using our proposed process, promising new use for butadiene is the conversion to styrene. As depicted in the figure on the left, the global demand for styrene has been steadily rising since 2009 and is expected to maintain a strong demand in the future. So the major products of our company currently include propylene, butadiene, and C4s. However, looking at the figure on the right, the value for each of these products is significantly lower than that for styrene and benzoic acid, which are the main products of the process we're proposing. And now I'm going to hand it off to Katie to talk about our process overview.
Thanks, Bryn. So the overall process to convert butadiene into styrene can be broken down into 4 main phases. The first phase of the process involves extractive distillation, which isolates the butadiene from the crude C4 stream. Within the second phase of the process, the butadiene is converted into VCHX, which is then purified to move on to phase 3. Within phase 3, the VCHX is converted into styrene and then goes through stage 1 of phase separation. In stage 4, the styrene is further purified to meet the 99.96% purity that's needed to obtain our sellable product, and this is crucial for our process. So in phase 1 of our process, extractive distillation was used to isolate the butadiene from the crude C4 stream. The extractive distillation process was outsourced for a capital cost of $165 million. Through this process, we were able to isolate 99.5% of butadiene to move on to phase 2. So for phase 2 of our process, 1,3-butadiene is converted into BCHX through use of reactor 1, which achieves a 95% conversion of BCHX. The reactor is 99.96% selective to BCHX over the side product, which is 1,5-cyclooctadiene. The reactor 1 system is technically 3 different reactors, one of which is a catalyst regeneration system for our process. In addition, cooling water is used to maintain the constant temperature inside of the reactor. The outgoing stream of VCHX and 1,5-cyclooctadiene enters S1, which removes any unreacted butadiene and any additional C4s in the distillate stream. This distillate stream enters another distillation column, S2, which separates the additional C4s that were left over from extractive distillation. This allows the unreacted butadiene to be recycled back into reactor 1 without the threat of buildup of C4s. The bottom stream of distillation column 1, which includes VCHX and 1,5-cyclooctadiene, enters distillation column S3, which separates these components respectively. The top distillate stream of S3 contains 99.9% BCHX, which then goes on to phase 3 of our process. I will be now turning it over to Sarah, who will be explaining the rest of our conversion process.
Thank you, Katie. Continuing from phase 2, we have our stream 9 with BCHX to be combined with H2O and oxygen and catalyst to go through reactor 2 to create styrene. The conversion of reactor 2 is 95%. This also comes with side reactions that create ethylbenzene, benzoic acid, benzaldehyde, and carbon dioxide. The reactor 2 is actually 5 reactors in parallel. 4 reactors are in use while 1 reactor is used as a catalyst regeneration. Then we have our gases and water to be flashed off with a 3-phase separator flash unit 1. Also, to note back on reactor 2, diatherm A is used as a thermofluid to minimize the temperature change across the reactor. Flash Unit 1 leaves stream 18 to be further purified in phase 4. And to go into more purification of water, we have a 2-phase separator, also known as Flash Unit 2, to take out the rest of the gases. And then we have distillation column 8 to take out the mixed contaminants to be used as fuel, while we have purified water at 99.93%. The water that is purified will be later recycled into reactor 2. So from phase 3, we have stream 18 with BCHX and all its impurities, with an inhibitor added to prevent styrene polymerization. S4 that will then separate benzaldehyde and benzoic acid to be later purified more, and the stream continues to be to distillation column S5 to have VCHX separated from it, where the VCHX will then be recycled back into reactor 2. Going back to distillation column S7, we have benzaldehyde and benzoic acid separated so that benzoic acid can be sold later, and benzaldehyde can then be used as fuel. So going back to S5 to S6, we have styrene and ethylbenzene as our main 2 components left, and ethylbenzene will be separated to be used as fuel, and the product stream 29 will have 99.96% styrene. So now we're going to go from the BFD to talk about some safety and environmental concerns. So first chemical that we have is 4-tert-butacol, and this is concerning because it can harm the marine life. It can cause nausea and vomiting, and the threshold limit value is 5 parts per minute. So then the next thing we have is our most toxic chemical, 1,3-butadiene. It has a threshold limit value of 2 parts per minute. Next we have benzoic acid, and as we said after reactor 2, benzoic acid is present throughout the whole process, so we made sure that our process has material that is non-corrosive. Also, something to keep in mind is that all workers there should have proper protection equipment. That includes goggles, hats, wearing full lab coats, and maybe a splash unit. So the inner battery limits make up $301.3 million of the total capital cost of $339.3 million. Our capital cost is sorted by phases, as we see in the BFD. Each phase includes direct, indirect, and rack and sewer cost. So our most expensive phase is phase 1 with $166.6 million because we outsourced our extractive distillation. For phase 2, we have $35.5 million, and most of the cost came from reactor 1. For phase 3, it cost $65.5 million, and most of the cost came from reactor 2. Phase 4 is $33.8 million, and the cost came mostly from the distillation column S6, which alone cost $15.2 million. So most of the costs were pretty high for the distillation columns because we had to consider the presence of benzoic acid, which is corrosive, so we had to use expensive non-corrosive material. And now we're going to pass it off to Li Yuanxie, who will talk more about the OBL.
Thanks, Sarah. I'm now going to talk about the outer battery limit cost. The outer battery limit cost makes up to $38 million to our total capital cost, about $340 million. It contains set development, product storage, and utilities. And the utilities also contain two parts. The first one is boiler upgrade, and the second one is cooling water increase. The total utility cost makes up to 70% for our total outer battery limit cost. And now I'm going to talk about our ongoing cost. Our ongoing costs are primarily for the raw materials, which is $572 million, and the second one and third one is the utility cost and the labor and overhead cost. Now I want to talk further for our utility cost. The majority of our utility cost is for the refrigerations, and we recycle many of our utilities like cooling waters and downstream aids, so we do not have to have much utility costs for those things. And we also recycle streams in our plant, such as high pressure steam and low pressure steams. So we do not need to purchase the steam, and it will save a lot of money. And now I'm going to the Remington to talk about the sensitivity study.
All right, thanks, Li Wen. Now, a sensitivity analysis was done on Aster with respect to styrene costs, raw materials, fixed and utility costs. The sensitivity analysis revealed that the after-tax rate of return, or Aster, was least affected by the utility and fixed costs. This was shown because it took a decrease in utility and fixed costs by about 30 to 40% for the after-tax rate of return to go above 12%. And it took a decrease of fixed and utility costs of 60 to 70% for the after-tax rate of return to go above 15%, which would be where we would like it to be. However, the sensitivity analysis also revealed that the after-tax rate of return was most affected by changes in the styrene price and the cost of the raw materials. A simple increase in the styrene price of 3 to 4% would increase the after-tax rate of return to above 12%, and an increase in styrene by 10% would increase the after-tax rate of return to above 15%. This is the same story with raw materials. A simple decrease in price of the raw materials by 46% would allow the after-tax rate of return to go above 12%, and a decrease in the raw material cost of about 9 to 10% would allow the after-tax rate of return to go above 15%, which is where we would want it to be. Now, the project's base case yields low NPV, low after-tax rate of returns, and low netbacks over the 15-year operating period. As we can see on the graph, the net present value on the y-axis and the operating year on the x-axis, nowhere during our 15 years of operating are we above a net present value of 0, meaning that this plant actually loses money if we invest in it. The after-tax rate of return is only 7.7%, which is far below the discount rate of 12%, and the net back rate just isn't where we want it to be. So these economic values do show that this plant should not be done because the economic values just aren't there. And now I'm going to hand it off to Corey, where he can talk about the alternative cases that we have done.
Thank you, Remington. In our first alternate design, we look at further purifying styrene from the distillate of column S6. This would require us to install another pump, distillation column, and heat exchanger, and we need to have all associated utilities as well. After modeling this in our Aspen Plus model, we found that we could recover an extra 500 pounds per hour of styrene. This would therefore increase our ATRR to roughly 8.5% and increase the net present value to negative 45 million. This design change is a simple adaptation as it affects no other equipment and is only an addition to the end of the process. Our second alternate design, we look at removing the large S2 column and replacing it with a simple purge stream. Here, we would remove column S2, get rid of all associated utilities, but we would incur some slightly higher styrene product loss in the end. As a result, the ATRR actually decreases to 6.5%, and our net present value decreases to negative 62 million. Taking everything into consideration, our team recommends not moving forward with the current project, as the ATRR and net present value are simply not high enough to justify the project. We would recommend moving forward with the other proposed projects with ATRRs of roughly 20% and net present values of 30 million. Our team would like to give out a special thanks to Mark Albro, Drew Draper, and Professor McFadden for the help and guidance throughout the project design. We'd also like to thank you for listening.